Hi guys, in this video we're going to do a quick follow-up to simplifying radicals as well as touch upon some a little bit more complex expressions that involve radicals. So with simplifying radicals, we're not just taking a look at something like radical 36 where it obviously works out to a nice whole number answer. We talked about in class being able to take an irrational number like radical 40, doesn't work out to a whole number, but being able to factor this such that one of the factors was a perfect square. So for example, 40 I can write as 4 times 10. I don't necessarily want to write that as 8 times 5 or 20 times 2, even though that would be correct factoring. Neither of those numbers would be perfect squares. If I write it as 4 times 10, I can then do this property of radicals, which is basically like splitting each of the factors, giving it its own radical. That's using the multiplication property of radicals. Radical 40 becomes radical 4 times 10. Right? It kind of makes sense there. We're not changing anything. But this bottom step is where we're really utilizing a property of radicals that's kind of defined like this. Imagine an equal sign between them. I'm running out of room here. Okay, multiplication property of radicals. Radical A times radical B is equivalent to radical A times B, all underneath 1. We could use that either direction. In the next problem in a second, we're going to use it kind of going the other way. Okay, so now what was the whole point of that? Radical 4 I can simplify to 2. And I get 2 radical 10. Now radical 40 and 2 radical 10 are equivalent. I can check this on my calculator, see that they both have the exact same decimal value to kind of tell me that I did this correctly. And now, kind of where we got up to, we talked about multiplying and dividing radicals. A simple way of thinking about this is multiplying just the numbers out front. So multiplying 3 times 5 to give you a new coefficient, if we want to call it that. And if we utilize what we talked about in the previous problem, you're allowed to multiply radicands, the numbers under the radical, to get a new radicand. And that's 160 times 2 is going to be 320. Okay, we're kind of doing the reverse of what we did in the last problem where we factored it. We're now multiplying it to give us a new radical. You wouldn't want to simplify this first. You don't want to sit there and simplify 160 because you might have to end up simplifying it again anyway. So you might as well just multiply first and then worry about focusing on how to simplify your product. So for 320, I could sit there and pull out something like rad 4 again. It's helpful to think about the largest perfect squares so you don't have to end up doing this 2 or 3 times. And you could test this through division, whether you use y equals, type in 320 divided by x, go to your table to see what factor pairs or basically what goes into 320. You could just sit there with division. Obviously we know this doesn't work, but if you want to test out perfect squares, hey, does 25 go into 320? Just see what works out to a whole number. If it works out to a whole number, you know it goes in. So to pause the suspense here, the largest perfect square, we know 4, we know 16, 64 actually goes in. And look at this, as soon as I write it, it goes in 5 times. As soon as I write it, I know I'm not going to have to do this again. Nothing else goes into 5. No perfect squares go into 5. If I pulled out a 16, I would have had a 20 hanging over. Okay, with 20, we could clearly see that 4 could also be factored out. So we got the largest with 64. We're going to use that factor property, give each one its own radical, and the perfect square we can simplify. Notice the number out front I didn't lose sight of. Okay, in each line I'm writing the 15. If you don't, you might end up making this mistake that we're not going to make right here, which is to multiply the 15 times the 8. They're both whole numbers. They're both being multiplied. Okay, 15 times 8, I can put 120. Radical 5. Once again, we can verify that this final answer and our initial values, 3 rad 160 times 5 radical 2, should have the exact same decimal approximation on the calculator. Don't lose sight of coefficients, or the numbers in front of radicals. They go along for the ride, and they're traditionally going to be multiplied by whatever you pulled out. When we pulled out an 8, or radical 64, that coefficient gets multiplied in the very last step. It's usually where people make a mistake. Okay, and this is what I really wanted to focus on. Problems like this. So we have 8 plus radical 48 over 4. So right away, and this is going to make a connection to quadratic formula problems that we'll see probably in a few weeks. We just start doing what we know. 48, 16 goes in 3 times. So I'm going to write it as radical 16 times 3. Okay, I split it up, give each one its own radical. Radical 16 I can make 4. Some of you that have some experience, you might recognize where this is going to in a few weeks, but knowing how to simplify these now is going to be a good thing. It's going to only help when we talk about completing the square and quadratic formula. So how do you simplify this? One way is to think about it as what it looked like before these two things were added. Think about them as like fractions that were pre-combined. In other words, there were really two fractions that had a common denominator of 4. We added together the numerators and we kept a 4. But if we unadd what I just wrote in blue like that, it's a little bit easier to see, hey, 8 over 4 is just simply 2. And 4 over 4 is just simply radical 3. In other words, we're basically, after we simplify the radical, we can simplify fractions in a traditional sense. Now, you're not just going to have to always do that and like unadd the fractions like I said. I've seen this written like this, and I like this trick. Make a little heart. Just to signify that all 3 of these components have to have a GCF for you to be able to simplify it. If one of them is off, you can't do any simplifying. So notice 4, 4, and 8, they share a 4. This only works if everybody, this only works if everybody has something in common. Deleting everything here. This would become a 1. Okay, obviously we don't put the over 1. That's why we just got 2 red 3 when we wrote it the other way. Now sometimes there's a denominator left over, as we'll see in a second example on the bottom below. But I just want to go over when this doesn't work. So let's say you have a problem like this and it says simplify. What you cannot do, let's stress this is incorrect. You can't do this. Cancel the 5 and the 10, say, oh, that's 5 goes into 10 twice. You can verify that on your calculator. You cannot do that because really you're simplifying or dividing out a GCF in one spot and not the other. In other words, the 3 guy was unaffected there inaccurately, not done correctly, right? If we're dividing everybody by 5, how does the 3 just get a free pass there? So very important that all 3 of those, and that's why that heart trick kind of helps. So if you had that purple question, that purple expression there, there's literally nothing you could do. It would be fully simplified. I suppose you could do this. Not that you had to. We could split it. And then if you want to cancel this one, now we can do this because it's separate. The 3 is no longer attached. Now I can say, hey, 5 and 10, I could do this. I don't know how that really helps you. I don't think this is that much simpler than what you originally had. But you could do something, I suppose. Okay, and just another example. So this one we're going to be able to do something. I'm going to start with the 75. I'm going to pull out a 25. I'm going to skip to each one having its own radical. 25 goes in twice. Okay, radical 25 becomes 5. Make a little heart, since you love to do these. Okay, all three have to share something. Do all three share something here? They 5, 15, and 30. I see a GCF of 5. So divide everybody by 5. Get 3, 6, and 1 left over. Now just obviously we want to write it a little bit fresher. We don't have to write the 1 as a coefficient. It's assumed to be a 1 all over 6. Okay? So with these fractional expressions, and these aren't just made up for the sake of doing them. Like I said, when we start solving quadratics, we're going to see that they usually boil down to something that looks like this fraction with a radical contained in a component. So knowing how to simplify them, very important. Very important that all three parts, drawing that heart can help, have a GCF, which they usually will. And if they do not, as we saw with this example over here, we cannot simplify them. Sometimes your gut tells you want to. You see 5 and 10, you want to make that 1/2, but you're ignoring that other constant that doesn't have anything in common. Okay? Just a quick little recap on simplifying radicals. Thank you for watching, and have a marvelous day.